but we also need to put talent in one
All right, so here's where we were yesterday. Once you click and close, have a look, please. So we were looking at.
Are you recording?
I am recording. Thank you for checking. We were looking at average rates of change versus instantaneous rates of change. What can you tell me about an average rate of change? Mathematically, what's that represented by? Slope of what kind of line? Secant line. That's the slope. So the average rate of change goes with the slope of a secant line. What's our definition of secant line? A line that's intersecting a curve in how many important places?
Two locally.
Two. Right. So that's what represents. Like if we're trying to find the average velocity of a particle between 2 and 5 seconds, that's where, here's our graph of the velocity function. So we've got velocity graphed on the vertical axis and time on the horizontal axis, right? And this ought to be useful. What's great about this? This is going to make your physics class, it's going to give it more teeth, because you guys are doing just an algebra based, you have to. Because it's, it's not, when I taught physics in McMinnville, this was great. We actually did the calculus based physics. We're one of two schools in the state that did this, and we did the required to be in calculus, or to be in physics, you had to be concurrently enrolled in AP Calculus. And so we did, like I had these backed up period to period, we had 70-minute periods, and so I had 140 minutes of calculus and physics combined. And so some days we would do it'd be a calculus day, some days it would be just all physics, but it went together so well. Man, it was awesome. But it gives you a lot more appreciation for the things you do in physics, because honestly, it's all kind of, and I don't mean this in a condescending way at all, this is just a high school class. I mean, it's an algebra-based physics class, but things have to be really sort of simplified and dumbed down to make them algebra-based physics. A lot of the relationships, you don't get nearly the full essence of the relationship, the physics relationship, if you're not allowing yourself to think of it in a continuous way, in a calculus way. If you're having to think of it in terms of, because what do you have to do in your physics class to do the class in high school as an algebra-based class? You have to make the assumption that the forces aren't changing, the accelerations aren't changing, and you'll watch, your problems will be that way. For a fixed acceleration, for a constant acceleration, you can do some stuff, but when you start to get these changing accelerations and these changing forces, then you can't do it. That's where you absolutely have to have calculus. And so really, physics is inherently a calculus-based thing. It kind of just changes it to make it algebra-based. So this, at least the parts that'll be applicable to the calculus we're doing, this will give you just a glimpse into where you're going to go with this stuff if you were to take a college physics class, for example, a calculus-based physics class. And even some college classes would be algebra-based physics classes. But if you were to do a calculus-based one, where would that take you? If you're thinking about engineering or physics or something like that potentially, or applied physics or some hybrid of those things down the line, and your future is going to steer you towards a higher level physics class, you'll get a little bit of a glimpse as to what that might look like, right? And so even this kind of a thing is pretty good. I mean, we're looking at a physics concept here. We're looking at kinematic stuff, right? So velocity. If we want to find an average rate of change, then we're just going to be connecting 2 points. We've got this point at t equals 2, and I got to remember, I think this is the one I want. Yeah, there's the point. And the point out here at, fix this, that's got to go back to, whoops, there. Yeah, 2 to 5, right? Between 2 and 5 seconds. So at 2 seconds, that's our instantaneous velocity. At 5 seconds, that's our instantaneous. Or actually, I'm sorry, this is position. I made this mistake yesterday too, didn't I? And I fixed it and I forgot to save it. Yeah, I don't want to confuse you. That would be confusing. Let me fix this. This is supposed to be, but I couldn't make it an X, right? I had to make it an S.
Yeah.
Because it didn't like the X. Right, it's a position time graph is what we're looking at. Did I mess something up?
You made those 2 X's.
Oh, I did, you're right, thank you. I was just seeing if you guys were paying attention. Okay, I think now we're good. So at t equals 2, our position is positive 1 meter. At t equals 5, our position is positive 8.5 meters, right? And if we want to find the average rate of change, well, all we have to do is, no, not that one, is connect those guys with a line. And how am I going to do that? I thought I had that done on here. I thought I did, didn't I? Is that it? Oh, there it is, right there. Yeah. So there's my line, okay? And I think I can even, like if I want to find the slope of that line, there it is. Okay, the slope of my line is 5/2. Makes sense, doesn't it? I'm rising by, is that right? Running by, doesn't seem right, does it? I'm rising by, oh yeah it is. I'm rising by 7.5 and I'm running by 3. No, that's not right, is it? Yeah. So, I must not be calculating the right slope. Well, I don't want to spend too much time on this. Let's see what happens if I drag this down. Oh, I think, hold it. That was right. Yeah, that was right. What am I doing? That was right. Yeah, I don't know what I was thinking. That's right. So the slope of the green line is just given to us by m here, right? And that, of course, it's, look, here's the difference quotient. It's our position. It's s of a plus h, right? And what's a? We're setting a to be 2, right?
Yep.
And h is I can't write delta x on here, so that was our delta x from yesterday. H is the difference in the x values, right? So we're going to move the horizontal spacing between the x values is 3. So I've got s of 2 plus 3, that's s of 5 minus s of 2 over h, right? Just rise over run, that's all that is. Slope of a secant line is simply a slope triangle, okay? And if this ought to look familiar, right? Just in general, go back to this for just a second. If I've got some random curve f, and I'm picking values at x and x plus delta x, well then if I make a slope triangle out of this, the run is just delta x. That's what I'm defining as the distance between the x values. And delta y is just the difference in the y values. So f of x plus delta x minus f of x. And so there's my slope of my secant line, right? Just rise over run is all it is, okay? But the challenge came, and here's where we left off yesterday. The challenge came with the idea that, we can easily calculate this, but what about an instantaneous rate of change? Okay, an instantaneous rate of change, and this was a huge dilemma. This was what's boringly titled the tangent line problem, and this was the impetus for Newton really inventing differential calculus, was coming up with a method for finding how are we going to come up with an infinitely accurate, not just a numerical approximation, not just something that's close or close enough, but something that's an exact value for the slope of a tangent line, right? Because we can do a pretty good approximation by just drawing the distance between the 2 points down to a very small value, and this is kind of what we talked about at the end of the period yesterday, right? Look what happens to our slope if we do that. We're getting slopes that are pretty close to the value that we think we're going to get. It's approaching probably what value?
1.
Probably approaching 1. So we could make an inference there that the slope of the tangent line is 1, but that's not good enough, right? That's not good enough, because what if it wasn't a value like 1? What if it was a value that was harder to come by, a function that was changing very rapidly? That's just not very fulfilling to have to do this based on a trend or an average, right? Or an inference. You want to come up with a way of doing this that's exact, because that's the way math works. And so we want to come up with the concept of the slope of a tangent line. Now we left off kind of talking about what's the definition of a tangent line? That's something you want to definitely have filed away. So there's 2 criteria. It intersects the function in one point, locally speaking. Could later on, it could be incidental intersections that we don't care about. But locally it intersects in one place, and it has the same slope as the curve. And that's a weird concept. Now, not until you get to calculus would you even say those words. What's the slope of a curve? Slope is a property of a line, isn't it? Right? But when we talk about the slope of a curve, what do we really mean? we talk about the slope of a curve, we're talking about the slope of the line tangent to the curve at the point of tangency, right? But it really does have meaning. If we were to zoom in infinitely far on a curve, so you flatten out the curvature completely, the curve actually becomes a line at that point then, right? And we saw a little visual example of that yesterday. And so our way to do that would just be to draw those together, but of course the problem is, and this is where we left off, and I'm just recapping at this point from yesterday. If we try to do that with a tangent line, you end up taking, if I let delta x shrink to 0, I get this indeterminate form, which is 0 over 0, which is, that always means more work, doesn't it? That's something that's not an answer we can accept. If we had a 0 only on the bottom, that would mean something that we could almost say, okay, we're done. That means it's infinite, right? 0 on the bottom and non-zero on the top would mean infinite. Or if I got a number like something divided by 0, that's 0. But if I get 0 over 0, it's indeterminate. We have to explore it further to come up with the exact answer. And that looks like stuff we've done in the past. And that's where we've tripped upon the idea of limits, right? We can solve this as a limit. And so the slope of the tangent line then just evolves from the slope of the secant line. It's just the limit of the slope of the secant line as the spacing between the points shrinks to 0 and the 2 points merge into 1, right? So we ought to be able to do something like find analytically the slope of that function. And I got to change this. I have v up here again. That should be an x, shouldn't it? Let's fix that on the notes. Maybe over here too. Okay, so let's try this. If we're trying to find the instantaneous velocity at time t, how could I set this up as a limit then? And this is pretty new. Let's see if we can do this based on our talk yesterday.
The limit of the difference.
Of the difference quotient, right? So we'll start off, remember that just in general, and I would always kind of start by writing down this template, right? The slope of a tangent line is equal to the limit of the difference quotient, which is going to be f of, I'll write it with x's at first here, right? X plus delta x, or h, whatever you want to call it. A lot of times we do write h in that. We'll start off with delta x. Minus f of x over delta x, right? In our picture.
Yeah.
Am I good with that? As delta x goes to 0, what's that going to look like in this case, where instead of f of x, we have x of t? We're finding instantaneous velocity, v of 2. Let's just find v of t first. That's even cooler. How can we do that? What's that going to become? We have to kind of make a mapping here. Instead of f of x, we have x of t. So what's the f become? X of t plus delta t minus x of t divided by delta t as we're going to limit as delta t goes to 0. Okay. So let's do this mathematically. We can do this. We have a function there. Let's start off with, what is x of t plus delta t? Here's my rule for x of t. Now think what that says. This just tells me, when I write this in function notation, right, this is what we're talking about in Algebra 2 right now. If I write this in function notation, all that says is that I'm inputting input values of t, and I'm applying this rule to calculate the output values for x. So what's x of, don't tell me an exact answer, but how would I calculate x of 5?
You put 5 in.
Yeah, I get 1/2 times 5 squared minus 5 plus 1, right?
Yes.
What's x of a?
1/2
Squared minus
A
A
plus 1. So what's 1/2 of the quantity t plus delta t? Same pattern, right?
Yeah.
You get that? We're just gonna get 1/2 times whatever I used to have for a t that's being squared, and then I'm subtracting it, and then I'm adding 1. Instead of inputting t or 5 or a, I'm inputting that entire quantity. So this whole thing right here is really just x of t plus delta t, right?
Yeah.
Minus x of t is just that. Keep forgetting the limit. So we just have some algebra to do. You prepare yourself for big time algebra. There'll be many times in here where we'll go through like 4 boards that are just another one problem, just algebra. We do lots of algebra and calculus. We just have to be careful.
That's how we do something.
Yeah, I remember doing something like this year.
So what do we get if I'm gonna power through this binomial expansion? What's a plus b squared? What's the pattern? A plus b quantity squared is a squared plus. No. Not Pythagorean theorem. If I'm doing the pattern, a plus b quantity squared
A squared
plus
2AB.
2ab plus, remember that, plus b squared, binomial expansion. Do you guys remember how to, like, Pascal's triangle? Did you learn that last year? Or in algebra 2?
Yeah,
Okay.
I don't remember.
2 years ago, wouldn't it? Yeah.
It's been a while.
We'll review that stuff when the time comes. So this is just, we're gonna get our 1/2 times, this is gonna be what? T squared plus 2t delta t plus delta t squared. I'll distribute the minus here, and I'm gonna get minus t minus delta t plus 1. And then over here, I'll distribute the minus and get minus 1/2 t squared plus t minus 1,
Yeah.
right on top, all divided by delta t. And this is gonna resolve itself pretty quickly. You can probably, if you kind of look ahead just a little bit, you can probably see what's gonna happen here. When I make my distribution of the 1/2, I'm gonna get a 1/2 t squared there, but look, over here I've got a minus, I've got a minus 1/2 t squared. Look, those are gonna cancel, aren't they? I'm gonna have the 1/2 times the 2 cancels, I'm gonna get a plus t delta t.
Yeah.
Okay? Plus 1/2 delta t squared, minus t, but look, I got a plus t. Those are gonna cancel. I've got a plus 1, but I've got a minus 1, so those are gonna cancel. Now look at that, I'm only left with 2 measly terms in that whole top when I cancel everything, right? Now I can't evaluate my limit yet.
Did you leave out a delta t?
Did I?
Yeah,
Minus delta t.
minus delta t.
Oh, I did. You're right, I did. So I've also got a minus delta t there. Okay, good. So I got 3 measly terms. If I try to evaluate this now, I'm still going to get, if delta t goes to 0, I get 0 plus 0, minus 0 over 0. But what can I do here?
You can factor
Factor.
delta t.
Yeah, and this is going to be kind of a pattern when you deal with these limits like this. When we're doing this process, and by the way, do you know what this is called? What we just did? Let me go back. So what is this? It is. We did mostly algebra, but when we calculate the slope of a tangent line, you've actually done your first big time calculus thing. Not big time it is yet, but we're touching the surface of a big time concept. You know what that really is called? That's a derivative, right? That's what this is. Finding the slope of a function at a point is the job of a derivative in calculus. And so we haven't actually given it that name yet, but that's coming. I mean, that's really the process that we did is technically what it means to be a derivative, okay? You heard that name, right? That's a big calculus word. Well, pat yourself on the back, you're doing your first derivative. So if we factor out a delta t, if we factor this delta t out of the top, what are we left with? Well, from here I get a t plus 1/2 delta t squared, oh, delta t, whoops. Minus 1, good, over delta t. And so I can vertically cancel those factors, and now I could evaluate my limit, couldn't I?
Yeah.
Okay, if I evaluate the limit as delta t goes to 0, well then, that term is going away, isn't it?
Yeah.
And what I'm left with is just t minus 1. That's a pretty simple velocity
That's
function.
2.
Okay? So we end up with velocity, which is, well, we know that that's instantaneous velocity is what corresponded to our function, right? You told me yesterday that if I have a position time graph, the slope of the position time function is its velocity, right? You guys have talked about that in physics, right? So now what we can say in terms of calculus is that now that we have this new derivative word that we can throw around and sound pretty smart, the velocity function, velocity is the derivative of the position function, right? And so we just calculated that our instantaneous velocity function, so we went above and beyond what we actually were asked to do. We found that v of t is equal to t minus 1. Now, all we set out to do was find the instantaneous velocity at t equals 2, but we found it for all values of t. How cool is that? I mean, that's amazing that we were able to do this. We came up with a function that predicts what the velocity is for any value of t that we plug in. So for our problem, all we need to do is plug in 2. V of 2 just equals 2 minus 1. There's our 1, right? That we saw numerically, we anticipated we were approaching the value of 1, but there's the proof. That's the exact answer, right?
Yeah.
Using algebra, okay? Okay, so let's make
I'm
this.
actually thinking all of this. With no
I
one
know, that's
else
what I was just
doing
thinking
it
about.
before you. You're just creating.
You're just messing around with numbers, trying to figure it out.
So let's try this one.
This first.
Okay, so now here's our function f of x. If we want to find the equation of the tangent line, well, the slope of the tangent line is what we need, right? The tangent line, the point of tangency is no big deal. What's the x value of the point of tangency? 1. What's the y value? 1, right? How'd we get it? Plug it in, right? We know that we know that f of 1 equals 1, and so that tells us that the point of tangency is the point 1, comma 1. We input a 1 and we output a 1, right? The hard part here, the part that we couldn't do before today, is coming up with the equation of the slope of the tangent line. Okay, so the slope of the tangent line, this is what we're going to call, if the original function is f of x, we're going to call it f prime of x. And that's one way that we can write derivative notation. So what that means, when I write f prime of x, that's a derivative. The f prime notation is great because what's that tell us? Prime in math means changed or evolved, right? So we started with our original function, and from that we evolved this derivative function that's giving us, that tells us, its job is to tell me what's the slope of the original function for every value of x. When I say slope of the function, that's exactly equivalent to the slope of a tangent to the function. If I draw a tangent line, the slope of the tangent line means the slope of the curve, right? And we know what the our method of calculating that was just taking the limit of the slope of the secant line. So I'll have you say it again. Everybody say it together here so you remember this. What is the derivative defined as in terms of a limit?
Limit of the difference.
Okay, what is the difference quotient?
Of x plus delta
Delta
x.
x. And I'm gonna go ahead and call it an h, just because I get tired of writing delta x. But it's, and in math, a lot of times mathematicians just get lazy. They don't want to write delta x each time, so they write an h.
Minus f of x.
All divided by
over
h.
H approaches 0.
Okay? And our job is just to do that, right? Okay, so let's do that. What's it look like for our particular function? And we always start general and then we become specific in calculus, right? So specific means this function. Okay, so what is it? What's f of x plus delta x?
Square root of x plus
Or x plus h, sorry, I said delta x.
Yeah.
X plus h minus, so that's that part, minus
Square root of x.
square root of x divided by
h.
Okay, and we're taking the limit of all that. As h goes to 0, okay? How do we do that one? Let's get practice. What do we do?
Square root of x plus h plus square root of x.
Okay, good, so we're gonna multiply by the conjugate.
Conjugate, that was.
Yeah, this is our, right, so.
That's not right.
So this is our, we want to find the irrational expression, so it's irrational because it's got square roots in it. And we want to rationalize the one that's causing the problematic 0, right? So we're going to multiply by the conjugate of the expression involving the square roots that is equal to 0. Now, if that weren't equal to 0, we wouldn't have to do it, right? But because we get 0 over 0, we have to. So we'll multiply this whole thing by square root of x plus h plus square root of x divided by itself. And I don't need to tell you this, but we're just multiplying by 1, multiplicative identity, same numerator as denominator, right? And what's that give us? On the top, we can do this really quickly. If I multiply conjugates, a plus b times a minus b.
X plus h minus x.
Okay, good. And the pattern is, if I multiply a minus b times a plus b, I'm just getting a squared minus b squared, right? First thing squared, first term squared minus second term squared. So that's going to give us our, oops, we lost the square root. That's giving us our x plus h minus x. And on the bottom, we get all this stuff, but that's okay, right? This is ugly, but it doesn't equal 0, right? So on the bottom, we get x times the quantity, all this stuff. Square root of x plus h. Say it again.
Wouldn't be h
H.
and x up front.
Out in front.
Oh, it is, yeah, I'm sorry, h, yep, yep. Times x plus, quantity x plus h plus square root of x. Okay, good. And now, if we simplify the top, what happens?
H.
Just get h. Good.
I don't like that.
So the h's cancel vertically, which leaves us with a 1 on top, right?
Yeah.
And now we can evaluate our limit. As h goes to 0, this h in here is going to disappear. And so what does the bottom become? Square root of x plus square root of x, which is what? 2 square roots of x. How about that? So we come up with our derivative function then, f prime of x equals 1 over 2 times the square root of x. And so the only missing ingredient in coming up with our line, we have a point of tangency. We just need the tangent of the curve, or tangent of the function, slope of the tangent line, at the point of tangency, which was an x value of 1, right? So the slope of the tangent line just equals f prime of, what color was our 1? It was a red 1. F prime of 1, which is, if I plug 1 in for x, what do I get? 1/2. And now this is really just like barely even algebra 2 stuff. It's almost algebra 1 stuff, right? We have a slope, we have a point. We're just going to come up with the equation of the line, right? So how do we do that? There's a bunch of ways we could do it. Remember point slope form?
Yeah,
Okay.
it's been a while.
Been a while. So if I do y minus a y value equals the slope times x minus an x value, that's a pretty efficient way of doing it. And honestly, in calculus, I wouldn't even care if we simplify it. I mean, it's a line. Whether I solve for y or not, it's a line, right? So we just get y minus, that was a 1, the slope was 1/2, that was a 1, and that's, drop a pen, that's good enough, really. I mean, you know, if specifically you're asked to write something in slope-intercept form, it's not hard to do. I distribute the 1/2 and add 1 to both sides, right? No big deal. But, and honestly, MathExcel might ask me to do that. On a paper test, I won't. On a paper test, I would just say, that's good. I mean, if we graph that, it's a line, okay? All right. So notations. Okay, let me go through this real quick. So these are all different ways of saying derivative. There's two that are really, three of them that we'll use a lot. F prime of x is really a good one because it reminds us that we're starting with a function and we're just adding a prime. So that's kind of the function notation for a derivative. You could also do, we would say this one as dy dx. That's how you'd say that, dy dx. Okay. And it just means the derivative of y with respect to x. That is, where do you suppose that comes from, dy dx? Yeah, slope, right? That's just related to, how do we define slope, right? Slope is equal to change in y over change in x. And why do we use a d instead of a delta? Well, delta is macroscopic, right? When we're calculating the slope of a secant line, we've got some, you know, I'll call it large. It may not be that large, but it's not infinitely small. We've got some real value of delta x and delta y that are sort of, you know, bigger than 0, right? What are we doing with the derivative? Well, we're shrinking those deltas. We're letting them approach 0, and so they become baby d's instead of deltas, right? That's a way to kind of think about that. And then there are some other, well, kind of a shortcut would be if we were to hybridize these two, a lot of times we'll just say y prime. So like if we had something like y equals 3x to the 4th minus 2x plus 1. You guys will know this trick really soon. The derivative we could just write as y prime equals 12x cubed minus 2. That's just a simple rule that we'll learn probably within a week. You guys will be able to see that. It's no big deal.
Okay.
We'll learn the derivative rules.
All right.
So I'll tell you what the roadmap is for derivatives. You got to go through the arduous process of calculating some derivatives using limits, just because it's a process that you're going to do. And I'm not just being mean. It's not just to write a passage or some kind of hazing, mathematical hazing ritual. It's there's a reason for it, because as you go through progressively bigger layers in calculus, what you're going to see is like really our class this year ought to be called calculus of a single variable. We're just going to look at calculus involving a function of a single variable, but you'll expand upon that in college, and you'll do things like multivariable calculus, where instead of finding tangents to two-dimensional curves like we've been doing right here, you'll be finding things like normal lines and tangents to maybe surfaces, right? So like you could have a two-dimensional topology. You know, it's three-dimensional really. It's a two-dimensional surface of a three-dimensional object, let's say. And you'd want to be able to find, let's say, the slope of that surface, which would be like if you're snowboarding or skiing, it'd be the fall line, so to speak, right? What's the steepest line of descent along the curve, which is going to vary as you move down the slope, right? And so as you move forward, to develop multivariable calculus, you're just gonna follow kind of a parallel path to what we do in single variable calculus, but you're gonna have to go through this whole limit process again to understand how it works. So I'm not just, like I say, I'm not doing this just to make you work hard. I'm doing it because I want you to become familiar enough with this process so that when you reapply this for a bigger concept later in your mathematical careers, you're comfortable with it, right? But having said that, we're going to go through this arduous process of doing it with limits, and then, of course, I'm going to show you the shortcuts, which make it really easy to do, right? And what you're going to find is derivatives, they probably seem intimidating now, but derivatives are just rules. They're really easy to do once you learn and practice the rules. Other parts of calculus get a little more challenging. Like the antiderivatives, the integrals are a little tougher than the derivatives because you have to kind of reverse engineer them. But the derivatives, eventually, we just come up with a bunch of rules that you follow, and you don't have to even do the limits. They're just like you memorize some rules and apply it. Okay? But it's the applications that are interesting. All right, what are we at here? 25?
Yeah.
Okay. So let's real quick, let's talk about, how about, what can I add in the last, would be useful in the last couple of minutes. We need to talk about where derivatives are defined. Let's get to it one more time. I think we did this fine.
What's the hardest problem you've ever done?
Okay, I did, actually, far more difficult than any graduate thing I did as an undergraduate in my quantum mechanics class. I had a problem set. I think I've still got this. I had 4 problems on it, and it was like 120 pages of algebra and calculus to get the differential equations to get this thing done. It was brutal. It was absolutely brutal. That was the hardest problem
Wait,
set I ever did.
120 pages per problem?
No, for all of them.
Oh, for
But I mean, it was
all.
pretty dense.
But still.
It was on squid paper. I mean, it was pretty dense. That was a brutal one. This guy was just cruel. I mean, it was terrible. He was just cruel.
Just notice it has white keys and you have black keys.
They could come together.